Hello students, here we are going to discuss about Young's double slit experiment. Previous module we discussed condition for constructive interference and destructive interference. Two sources S1 and S2, they are coherent sources made from the source S. The waves from S1 and S2 interfere each other and we are getting alternate bright and dark bands on this screen. These bands we call as fringes. Now see, from S1 and S2 waves are advancing in the forward direction. Here the continuous line represents crest and dotted line represents trough. When the crest falls on the crest of one wave, there constructive interference takes place and bright band is formed. If the crest falls on the trough of other wave, dark band will be formed. That is the case of destructive interference. Between two dark bands there is a bright band. At the center O, all the waves reaching and in same phase. There is no path difference or phase difference between the waves from S1 and S2 at the point O. So O corresponds to maximum, that is the bright fringe, that is the central bright fringe. This is Young's double slit experiment. Here see the distance between the plane of the slit and the screen, that we will use the letter capital D, and the distance between S1 and S2, that we will use the small letter D. Here S is the source, main source. Now we will see the schematic diagram of the previous experiment, that is S1 and S2 are the sources, coherent sources, and now we'll see here what is capital D, distance between the screen and the plane of the slit. What is small d, the distance between the coherent sources S1 and S2. Then at the point P, the waves from S1 and S2 reaches not in phase, because here there is a path difference of S2A. We will calculate how much is the path difference between the waves from S1 and S2 to reach the point P. This path difference is S2A. Here we took a point P at a distance y from the center of the screen. Now see, here the path difference is equal to S2P minus S1P. See, what is S2P minus S1P? That is S2A. See the diagram here, that is S2A. From the diagram, we know that sin theta, if you take the triangle S1A S2, then what is sin theta? Sin theta is equal to S2A divided by S1 S2, because this is 90 degree, so S1 S2 is the hypotenuse. So sin theta is equal to S2A by D. S1 S2, the distance I told you, that is small d, that is S2A is equal to D sin theta. When theta is very small, so we can take sin theta is equal to tan theta. Then from this triangle P, from this triangle we can take it as, what is tan theta? Tan theta is equal to OP upon D. OP upon D. That is tan theta is equal to Y by D. We can say that tan theta is equal to Y by D. Then the path difference S2A, that is delta, that is equal to D sin theta
Sin theta is nearly equal to tan theta, and he has seen that tan theta is equal to y by d, that is dy by d, d into y upon d. Then if the point, this point P is at a distance y from the center O, if the point P is a bright point, we don't know the point P is bright or dark, but if the point P is a bright point, so what we will do, we will equate here the condition for constructive interference, that is dyn upon d. Yn means the position of nth bright fringe. Yn means position of nth bright fringe. Dyn upon d is equal to n lambda, that is yn is equal to n lambda d upon d. This is the position of nth bright fringe. Now we will go for n plus 1th bright fringe. So yn plus 1 is equal to n plus 1 into lambda d by d. You know that between two bright points dark fringe is there. So we want to find out what is the fringe width of a dark fringe, that is beta. Yn plus minus yn, we will get lambda d by d. Nth dark fringe. For nth dark fringe, dyn by d, that is equal to 2n plus 1 into lambda by 2. So we equated it with the destructive interference condition. That means previous case we discussed what is the condition for destructive interference. Then their path difference is equal to 2n plus 1 into lambda by 2. So that path difference and path difference we got here, that we equated. Then the point P is a dark point. Then we will get the equation yn plus 1 by d, that is equal to 2 into n plus 1 plus 1 into lambda by t. Then n1th position of a dark fringe and nth position of a dark fringe. We subtracted both. We got the fringe width of a bright fringe, that is lambda d by d. We can see that fringe width of bright fringe and fringe width of dark fringe both are same, that is lambda d upon d. Lambda is the wavelength, d is the distance between the plane of the slit and the screen, and small d is the distance between the coherent sources. We have seen that fringe width of bright band, that is equal to fringe width of dark band. Beta is equal to lambda d upon d. Beta is directly proportional to wavelength of light. Beta is directly proportional to distance between the plane of the source and the screen. Beta is inversely proportional to distance between the sources, that is small d. If we conduct this experiment in water, we know that the wavelength of light in water decreases, that is lambda dash is equal to lambda by n. N is the refractive index of water. Beta is directly proportional to lambda, and now the wavelength decreases, though what happened to the fringe width? Fringe width decreases. The wavelength decreases, so fringe width beta decreases. Here the linear fringe width beta is equal to lambda d upon d, and angular fringe width theta is equal to lambda by d. Very important point, the linear fringe width depends upon capital D, but the angular fringe width is independent of capital D. That means if we change the distance between the plane of the source and the screen, the angular fringe width will not change. Now we have to see what is the shape of interference fringes. The shape of the interference fringes is usually hyperbolic, but sometimes it is straight when the
distance between the plane of the source and the screen, that is capital D, is very much larger as compared to the fringe width beta. Next, the distribution of intensity. Here we have seen that the fringe width of dark band and bright band both are equal. See here, the fringe width, the width is same, alternate bright and dark band. And here what it is shown, x-axis the phase difference shown and y-axis the intensity shown. Intensity of all the bright bands, it is same. And say when pi, that time the dark band is formed, then 3 pi, 5 pi, that way the dark bands, and that is our 2n pi, 2n pi, n is equal to 1, that is 2 pi, n is equal to 0, that time this bar, that is the bright point, that is the central maximum. Here the width of the central maximum and all the other bright, it is same only. Now, interference and conservation of energy. You know that interference is the redistribution of energy. Some points it is dark and some points it is bright. In the dark points, the energy is disappeared, but bright point energy appeared. That means energy disappeared in the dark points, appeared in the bright point. So the energy is conserved in the interference case also. Now, what are the conditions for sustained interference of light with a good contrast? First one, the two sources must be coherent source of light. What is meant by coherent source already we discussed. Then, two sources of light should emit light waves continuously. Two coherent sources of light should be close to each other. That means the distance small d, it will not be that much large. The amplitude of two waves emitted by the two coherent sources of light should be equal to get complete contrast between the dark and bright bands. See, if the amplitudes are same, then at the minimum point you will get a complete darkness. The two coherent sources of light should be very narrow. If the sources should not be narrow, then you will get a uniform illumination on the screen. Then distance of the screen from the coherent source of light should not be small. The light is to be monochromatic. If the light is monochromatic, you will get a good contrast between bright and dark bands. If it is a polychromatic light, if you use white light, you will get all the color fringes there. So the fringes will not be clear.